Okay, hi guys, welcome back. So today we are moving on from convolutional. We're going to a recurrent neural network, and I'll let Chongmin introduce this.
Hi everyone. So welcome back again. So today will be a continuation of what we have learned the previous few times. So the network structure we are going to look at today is called the recurrent neural network, as what Chikin mentioned. So let's just this is the introduction slide again. For those who are new, the idea is mainly the concept. Okay, the math I will not touch too much, although I will point the resources for you all to take a look at the further math if you want to. Recurrent neural networks have the most math out of all the networks I've studied so far. Yeah, because it deals with like recurrent time series, and like because of that, the backpropagation is very complicated. It goes through several time steps. Okay, but the idea is to look at how it works and then understand based on the diagrams that I will be showing how it works. Okay, then at the end of this, we will have a practical coding session. Okay, the code should already be shared with you all. So later I'll just be stepping through the code. Okay, so you can interrupt me anytime if you want to ask any questions, because I believe that a friendly conversation is actually good for understanding as well. Okay, so this is the ground rules. Okay, so this is what we have studied so far. Recall that a neural network is mainly made up of like neurons connected to each other, and one of the most basic models, okay, or rather an extension of the basic model. A basic model is a perceptron, which is one layer. Okay, a multi-layer perceptron has multiple hidden layers, mapping an input to the output. And the characteristics of this is that it is fully connected in its connections from each layer to another layer. So you can see that like this blue node connects to all the green nodes in the next layer and so on. So this is a multi-layer perceptron. Okay, then we also covered through convolutional neural networks the last few weeks. Convolutional neural networks, the main thing is that instead of having this fully connected scheme that you see here, you don't connect everything. Like you connect only some. Remember, you like, let's say for example, you connect to this two, and then the next node you also connect to this two, like the two neighbors or something like that. Yeah, so this is like called like a filter operation. And there's also another interesting thing is that they share weights. So like for example, the right weight might be shared for all of them. You apply the same filter throughout. So this is the rough gist of a convolutional neural network. There's a more sparse connection and there's shared weights. So this helps to find out features in the images. And this is more suitable for domains where you have two-dimensional or three-dimensional, where you have your neighboring pixels or neighboring structures more important than the rest of the structures around you. Okay, then you use convolutional neural networks. So this is a recap. Okay, rather today we'll be covering recurrent neural networks. Okay, so what is a recurrent neural network? Okay, this is a normal MLP so far, but a recurrent network, apart from just having this fully connected, in fact, actually this front part here can be CNNs also. I mean, it really depends on what you want to do here. But the idea of recurrent neural network is really, let me just highlight this. The idea of recurrent network is this part here. You have your node, okay, and then as you pass the input through time, okay, over here, this is only time step 1. Okay, if let's say we were to show you time step 2, this will be the same diagram again. But the idea is the node at time step 1, okay, it will feed itself some information again when it goes to time step 2. So it's like, you know, if you play a game like an RPG or what, you develop your character, right? Then after you develop for one day, the next day your character still like has some of the stats from the previous day. Yeah, because so there's some information that's passed on from the previous time step. And that is the key highlight of a recurrent neural network. So there is actually also invariance here. The thing is, however long you unroll your network for, in terms of you step through your data sequentially, however long your sequence, the way you process this node here, this purple node here, is the same because the weights don't change, okay? The weights of the nodes used for this recurrent neural network will be the same weights regardless of time steps. Okay, then that preserves some form of sequential invariance. Okay, and that's why it's so popular. Okay, I would like to do a caveat here. It's so popular in the past for like natural language processing or sequential models. Okay, so today we'll be just covering more on this. Okay, but I would like to say that this kind of network has some merits in the sense of the invariance in sequential in time. Okay, but it has been like outclassed in like 2017 by the next model called transformers. Okay, so this when we come back from the long holidays, we will cover this transformers. So transformers has been taking the natural language processing by storm. Basically, instead of using sequential inputs, they put all the inputs at one go and then use some form of attention to decide what to focus on. So that's the key idea of transformers. I'll be touching more on this on another session. Okay, so I just want to let you all know that back then, 10 to 20 years ago, until like 2017, this was the dominant structure for sequential models. After that, it became this transformers. Okay, and who knows what kind of models will come out after that. Okay, but you will see that there's some parallels between both these models. So we won't be exactly wasting time just talking about recurrent neural networks. There's some stuff to learn from it as well. Okay, so as usual, the idea is to learn what makes up the strengths of a recurrent neural network and then see how we can apply it in even future models or other contexts. Okay, any questions so far before I move on? Okay, I'll just pause at this slide. Okay, if no questions, oh, sorry, is there anyone wanting to ask something? Okay, if no questions, I will move on to, okay, so when do we want to use RNNs? Okay, so as I mentioned earlier, you need to want to use it when you have some form of sequential data. Okay, it is natural to want sequential data because an RNN takes in inputs over multiple time steps. If you only have one time step, it is no different from an MLP or just a normal feed-forward network. But because it has multiple time steps, okay, then you can use recurrent neural networks because it can take into account all these different inputs at different time steps. Okay, and another criteria is that because we take in the input sequentially, your output to your model at that particular time step should only be dependent on your earlier data in the previous time step. So if you want to do stuff that you can essentially use the information of your whatever you fed in the model previously to predict the next time step or to do some sort of generation at the next time step. So because of that, there's this kind of limitation. Although there's another kind of RNNs, which I won't be covering today, that is called bidirectional RNNs. You can look forward and look backwards. So that you actually don't have to require like this rule of only earlier data. Okay, but that's the basic form of an RNN. You only use the data from the previous time steps. You don't get to look ahead into the future and see what's going on. Okay. So the last thing that makes you want to use an RNN is that regardless of your time sequence, the way you want to process your data will be the same. Okay, so this is something like, for example, stock prices, how you process the data is based on the previous trends. It doesn't really change across time periods. I mean, that's an assumption, of course. Yeah, because if it was so good, people will be all rich already. But of course, an RNN, people have tried doing stock prediction. It didn't really work out too well. Okay, but the idea is, as long as you can process the data the same way, like for example, a sentence, like if you were to use the same way, so like let's say I were to take a look at this line here, the way to process the data is the same through the sequence. Okay, if let's say I were to use this sentence here, and then I like swap the position of the sentence here, okay, assuming that these are like bullet points or what, it doesn't matter whether I process this sentence first or process it last. Okay, in this kind of context, okay, in your input, if I were to swap the bullet points here, the output would be the same, because if I were to use like RNNs wise in order to do like prediction, you will process data in the same way, like in this time period as well as in the previous time period. Okay, of course, if we add in the hidden states or we add in the information from the past, things would change. Okay, but the idea is we want to process stuff in the same kind of way, like now or later. Okay, so yeah, this is some of the considerations when you want to use RNNs. Okay, so now we talk about like the types of RNNs that are available. So these are the types of RNNs right now. Okay, so based on the graph you can see here. Okay, by the way, most of my slides are taken from the Stanford CS231N module. Okay, you can find this online. They shared their slides online. I thought their slides were quite nice, so I used quite a lot of their illustrations. Okay, but now let me just explain what this slide means. So if it's a one-to-one relation, it means that your input has only one time frame, and your output has only one time frame. So you can see that this is no different from like a neural network. like an MLP where you have input and output over one time step. Okay, but once things start to get quite interesting, once you have multiple time steps, like you have time step 1 here, time step 2 here. So for example, image captioning. Okay, image captioning, you pass it only one image at the starting time step, but then you want it to generate like different text at the end. So like you can have the text like a bird is on a branch. Yeah, so maybe at the first time step it will come out, then a bird will be the second one, is on a branch. Then at the end of it, it will probably output like a CLS, like closing time step, basically a symbol to indicate like end of sentence. Yeah, so these are the kind of applications for one-to-many. Okay, many-to-one will be like if you have many different inputs at the first few time steps. Okay, so, and then only have one output towards the end. So like one kind of situation that this can be like sentiment classification, where you have like a series of words here, like the earphones are so good. So then your output here will be like maybe a sentiment analysis where you can say that the customer is satisfied. So you have like different kinds of output classification for this. So people use this for like forum to analyze whether certain text, is it good, is it bad, do sentiment analysis. People also use something like this to find out whether something is spam or not. You can put the whole input sequence and then out comes whether is it spam or not spam. So you can use this kind of things to classify. Okay, then next we have many-to-many. So many-to-many is something like language translation. What happens is that you put in an input text here. Like for example, you want to do like let's say English to Chinese, okay, or English to Japanese. Yeah, so like it can be like I am a boy, or I am John, and over here will be like, if you translate this one, will be watashi wa John. Yes, something like that. Yeah. So it's like that. Yeah. So this is the kind of things that are used for language translation. Okay, so there's last part here is called many-to-many. Many-to-many is something like you input something and then you want a certain output at each frame. So this can be something like a frame level classification of like maybe if you have a series of frames, for example, like you want to predict the motion of a ball. So your first frame could be like this. Your ball is here. Your second frame, your ball is here. Your third frame, your ball is here. So for example, at the input frame, this is your input. My output frames, what I want to do is I want to predict maybe the future position of the ball. So my output frames here will be like the next position. And then this one will be like this position. And then the last one here, maybe the ball is like somewhere here off the screen. So you can use like this kind of things to do this kind of sequential like look ahead predictions for images. Or in terms of like classification, you also can classify whether like this image has a human, has a dog. Sometimes the sequence helps in order to generalize some form of context. Like just a single frame may not be good enough. Okay, then in that kind of context, you can use RNNs. Okay, that's also why I say that RNN itself is not exclusive from CNNs, because RNN part is just this like green part here where you go through time. Okay. The thing is you can also put architectures such as CNN here. Yeah. In fact, people have done even more complicated one. They do like CNN come here and they also do CNN out here. Yeah, so it really depends on your kind of use cases that you want to use for. But the idea of recurrent neural networks is really that instead of just looking at things only from one time frame, which is like the image classification kind of problems where you only have an image and you classify it. What if I look at multiple images through time and then I can get some form of information from those images in the past? Then those kind of situations, RNNs would be helpful. Okay, just do a quick pause here for any questions. Okay, so I would like to highlight one thing here. Okay, that I just want to say here right now. Okay, the limitation of RNN, right, is actually, you see this green arrow here, the information at each state that you process over here. Okay, I'll cover this in detail later, but I just want to highlight this right now. the amount of information that you have at each time step, okay, is purely just based on the hidden state here from the recurrent neural network node, plus the input here. Okay, so you actually don't really get all these inputs here. Like all these inputs here at time step 1 will be discarded, okay? Because you only can get the current time step input plus the hidden state from the previous node. So if you all know like information theory, there's actually a form of bottleneck, and the bottleneck is actually here. Okay, because there's only so much information your hidden state can contain, but your hidden state must actually contain all the information from all the previous time steps. Like for example, if you were to look at this hidden state here, this hidden state must encompass every single thing that has happened before. So can you all see that as we progress in time steps, can you all see that this vector h, which is a fixed size vector, will actually have a lot of difficulties in trying to learn everything that has happened. Yeah, it's like you have a limited memory. I keep giving you numbers to remember. Eventually, you will lose some form of information. Okay, so this is one of the drawbacks of RNNs, okay, which transformers try to solve. Okay, so I'm just giving you a form of like some primer in terms of like why RNNs didn't work out too well. Okay, but for the last 20 to 30 years, it has been the dominant architecture that most people use. So there's still some use for this architecture. It's just that the problem that I highlighted earlier, the bottleneck problem, proved to be quite a difficult one to solve. Okay, that's why RNNs didn't really achieve that big a breakthrough back then.
Can I ask, so at this stage, right, what you're talking about is if there's a very long sentence, the last node, it's not good. Like the prediction will not be good on the last one if it's a long.
Correct. Yeah. So there's this issue where like if you have a very long sentence, you want to fill up the next word. So I mean, I give you this example. The cat which sat on the back took fell on. So you have this thing here, right? So I mean, it has to do with the cat, but you have a very, very long thing here. So this is like super long stuff. And then after that, you need to have the phrase over here, right? So this is actually linked to the cat over here. Okay, so maybe this is its or her legs. Okay, depends on how you classify it. But the main thing is if you were to use RNNs, the longer this part here goes, the harder it is for information at the front to flow through all the way to the end. Okay, because of the way this hidden state is propagated. Okay, you have to make a very, very intentional, you need to like give yourself a form of focus so that you still remember this kind of important things from very, very early on to use to predict the next word, maybe quite far down in the sentence. So that's indeed one of the drawbacks, which later I will share some of the architectures for RNNs that try to solve these drawbacks. Namely, they are called the long short-term memory, LSTM, and the gated recurrent unit, GRUs. Okay, so we have tried to use this to solve it. Okay, but as I said earlier, transformers still beat all of them. So yeah, you will get to know transformers the next time I talk about it. Yeah. So yeah, Chicken, you're right. The longer the input sequence, the harder it is to remember something that is in the earlier part of the sequence. Okay, anyone else got questions? Notice I haven't touched on any equation, but I think this slide should be sufficient to let you all know what RNN does already. Okay. Any other questions so far? Yeah, because I hope y'all will be able to finish this this set of presentation. It's going to get a little bit more math in the next few slides. Okay, but I think these are essential math to understand what's going on.
Just want to check, right? So this is one layer. The green layer is one layer. You can put many of these layers stacked. together,
Yes,
right?
correct. You
So
can stack multiple green
but
layers.
like, is it better to stack, or does the efficiency degrade
Okay.
over the linear?
Typically people have found like for more complicated problems, stacking like 2 to 3 layers might help with the performance because the next layer is able to take in the inputs, the outputs from the first layer. And like, it's something like RNNs. You start from the small features and then you build up more and more complicated features. There's shown to be some form of benefit to do that for RNNs. But if you stack like 4 or more layers of hidden recurrent networks, it doesn't work very well. So there's some form of gradient propagation issues here if you stack more. I mean, maybe it could be solved if you use some form of like skip connection style where you skip certain layers. But then again, it is quite hard to implement all this, and it takes a lot of hand effort to fine tune. So typically people don't use too many layers for RNNs. Max I've seen is like 2 to 3. Yeah.
Okay, thank you.
I don't know. We have an NLP expert here. Any tips based on your experience?
Yeah, good is here. Oh,
Yeah, it's okay. I mean, just feel free to talk along the way. Okay. If nothing else, I'll move on. Okay, because there's still some more slides to cover. Okay. So, okay, welcome to the math. All right. So for RNNs, okay, the formula that we normally use for RNNs is this. Okay, H refers to the hidden state. Okay, the hidden state is a function. Okay, a function. Whenever you see the word function, it means like neural networks, because neural networks approximate a function. New state is a function of the old state, like ht minus 1, and the input vector x at that time step. So remember, I drew the diagram earlier. So if you look here, what it means is that this new hidden state here, ht plus 1, okay, is basically a function of the previous hidden state h, okay, and the current time step x t. So you can see that xt, okay, actually this is not ht plus 1, sorry, this is ht. So the current time step ht, oh, I deleted, the current time step ht is a function of the previous time step ht minus 1 and the current input xt. So you can see that, like, if you look at this as one node here, so these two are your inputs, and then this ht will be your output. Yeah, so a recurrent neural network basically takes in the past information plus the current input at that time step and gives the next hidden state. Okay, so this is the basic of the recurrent network. Okay, I hope this is clear. So this is the key equation that we need to know. Okay, so of course there's this output y also. So actually there's another equation here that is not shown, but basically yt, the output at that particular time step, is another function. Let's call it function y. Okay, it's a function of whatever is in this thing, which is basically is a function of ht. I mean, of course, you can use the previous hidden time step as well, but usually the output function is just based on this thing here. Yeah. So usually this is the equation for an RNN. I'm clearing the drawing. Okay, so what does this mean in a neural network? Oh, it's here. Yeah. What does this mean for a neural network? It means that if we translate this to a neural network, we can translate it to like a non-linear activation of your weights. So we have a set of vectors here. So WHH stands for the weights, okay, from the hidden layer to hidden layer. So the dimensions are the hidden layer dimensions. This WXH is the dimensions that map the input layer X to the hidden layer H. Okay, so you can see that after you do this two matrix multiplication, okay, the dimensions for this output will be the dimensions of your H, because of the way this matrix multiplication is done. Okay, I don't want to go through the details for that, but the idea is that we take in both the input, okay, the input from the previous time step, oh, sorry, we take in the input from the previous time step here, plus the input from the current input. And then we just basically sum up both inputs, pass it through a non-linear activation function. Okay, remember why we need a non-linear activation function, right? Because if you just use linear, then the entire model becomes just a linear model. So you need to use some form of non-linearity. So over here, 10H is used. Okay, why 10H? Right? I mean, some of you all might ask why 10H, right? I mean, you can also use sigmoid, or you can use I don't know, cosine H. I guess it's just because like this is convention. Yeah, you can try other activation, non-linear activation function. It should still work. Okay, so this is the hidden state. And then lastly, we have the output. If let's say there's an output at that particular time step, the output is based on a weight vector that takes in that maps the dimension h to dimension y. Dimension y is the output layer dimension. So this is the weight vector that maps in the hidden state at current time step t to the output. So this is a rough idea of how an RNN works. And yeah, of course, you all know how these weights are trained. This WHH, WXH, and WHY. Okay, so they are trained through backpropagation. Okay, of course, the backpropagation is a little more complicated. Okay, actually, it's not a little more, it's quite a lot complicated than the normal networks. Okay, because you have to go through multiple time steps backwards. Okay, I'll show you all the diagram later. Okay, so if let's say we want to have, like, this is the most complicated kind of RNN. Okay, if let's say we want to, okay, let's just focus straight on the input layer first. Okay, so the input layer is here. So we have our input layer. This H0 is the initial hidden state, usually set to random. Okay, so we can just put this as random because we have no information yet. We can just put the hidden state as random. It doesn't need to store anything. Or you can put a hidden state of all zeros. Okay, so it really depends on your use case, which one is better. Okay, over here is my input at time step 1. So at input at time step 1, I'll pass through my RNN unit, which is represented here as a FW. Okay, which basically implements the weight vector that multiplies this H, the weight vector that multiplies this X. Okay, and then this will go to the combined dimension of your hidden layer dimension here. So we do this for all the time steps. Okay, so we do this once over here. This operation, we do it once here. Okay, we repeat the same operation again over here. And we repeat the same operation over here. So you can see that actually this function FW, you can see that this FW doesn't change at all across time steps. So that is what I mean by invariance across time steps. The way you apply your function is always the same. Okay, but why do we get different outputs? Okay, anyone want to guess? Okay, if we apply the same function at each time step, why is my output different? I mean, how can my output like Y1, Y2 be different? Anyone want to give a try? Like we are just doing the same function. Why would there be different outputs? Okay, yeah. Why would this output Y1 be different from my output at Y2? I mean, I'm just using the same method to give the mapping of my input and my hidden state. Anyone want to try? Like, why do you think we can get different outputs if we apply the same function at each time step?
Is it because the input is different, like x1, x2?
Yeah, correct. So although your function is the same, but your inputs to the function, your hidden step, your hidden state at like H0 and X1 is different from like the hidden state. It can be different from hidden state 1 and X2. So because of this difference, you can use the same function, you can end up at a different part of the function. I mean, if you were to draw a function like this, okay, you have a function that maybe is like that. So at different parts of the input, we're going to get different outputs. Yeah, so although your function can be the same, and take note, this is a very complicated function. It's not like 2D like what I drew here. Okay, if you have a function here, okay, as long as we have different combinations of like input time steps like H0 and X1, you can have different parts of the space here. You will get different like this is H0, X1. You will get like different outputs here, like this is H1. Yeah, so because of stuff like this, although you use the same function, you actually get some benefits of so the benefit that you get out of this is that because you know the way you process your data is going to be the same regardless of time step. So you can actually learn these weights here. So can you see some similarity between this and CNN? You actually learn these weights here, FW, you learn it concurrently. So regardless of time step, your FW is updated across all the time steps. So it means that you actually learn faster. Like you don't need to wait until like a particular part of the sequence that you learn. Imagine if you don't have these shared weights, then you need to learn the same input-output relation for every single part of the sequence. Okay, that will take a lot more training data to learn. Okay, but assuming you already know that the way you process the sequence is going to be the same regardless of where the sequence is, then learning this way will be much faster. Okay, so I hope this is clear. Okay, then we look at the loss function. So you can see that the loss function here, okay, the loss function here is typically any loss function you want to use for your particular use case. But if you have multiple loss functions, okay, what you can do in order to train the model jointly, okay, this is a very common trick if you have like a model that has multiple outputs. Okay, in this case, the model has multiple outputs. So you can see RNN is actually quite a complicated model. This model has multiple outputs. How do you train them together? Very simple. You just basically put them to a combined loss function. You can even do a weighted loss function if you want to, but the idea is to just put all of them, you add them up to a particular loss function. You just add them up together and you just train using this loss function, which will then, because of the beauty of backpropagation, as long as all your operations that you use forward is differentiable, okay, you can okay, as long as the functions are differentiable, you can learn the weights. So that's the cool thing about backpropagation. Okay, I've gone through quite a bit of technical stuff here. Any questions so far? Okay, I hope you all understand this because I'm not too sure like whether my pacing is a bit too fast. But yeah, this is the rolled out view of a recurrent neural network. Okay, now let's go through an example. Okay, so this example we will also go through in code later. So this is called a character level language model. So in a character level language model, basically you are like trying to predict the next letter given the first few letters. So we have an alphabet or a vocabulary consisting of these 4 letters, H, E, L, and O. And then basically, for example, we have a word hello. So given this H, E, L, L, we want to predict the output, the next character is called O. So we want to do that. So how do we do it? Okay, firstly, the network is not going to recognize characters like that. You know, if you want to have a differentiable operation, you cannot use like strings or characters. So what can be differentiated? Numbers. So you need to convert this to numbers. Okay, of course, one way to do this will be to use like some label encoding where you like label 0, label 1, label 2. But you know, neural networks, they don't work quite well using this kind of ordinal values. So typically what is done is like you have some form of layer where you represent them in a different format. So in this case, what we do is one-hot encoding here. You can also do an embedding layer, which we will see later in the code. So you can either do a one-hot encoding or you do some form of embedding to like make the character go into some n-dimensional space that has some meaning in terms of of where the characters are. Like in the n-dimensional space, certain words can be together, certain words can be like semantically apart, certain words semantically away. Yeah, I won't touch on this because I'll leave this for the transformers part. Okay, so this is the first layer. The first layer just puts them into one-hot encoding. So are you familiar with one-hot encoding?
Maybe you just summarize one-hot encoding.
Okay.
But
so yeah, one-hot encoding means that there's only going to be one. Okay, it's not a pun here. There's only going to be a single one. Okay, in this vector. So this single one represents like the particular character here. So like this may be a H, E, L, and O. So one appearing here represents this is a H, a one appearing here represents this is an E, a one appearing here represents this is an L, and a one appearing here represents this is an L as well. So this is how we do like one-hot encoding. Okay, next up. Okay, we go to the hidden layer. So the hidden layer, remember, it can be some form like this, where you use like a non-linearity plus some weights of the input and the output. So you see, although we use the same function, you see that the hidden layer is generally different, okay, in terms of the, of course, this is a fake example. I mean, okay, this is like a toy example. But in general, when you run the recurrent neural network, you will notice that the hidden output activations, or rather the HT that you generate at each time step, will generally be different. Okay, so this is how we get the hidden layer vectors. Okay, so you can see that over here, the hidden layer is of size 3. So it means that, I mean, some math here, okay, let's say this WHH. So this is a 3x3 vector, a 3x3 matrix. This HT minus 1, you can see that this could be like 3x1. Yeah, so in the end, when you multiply this, you will get something like 3x1. Okay, matrix multiplication. So you will get like a series of 3 vectors. This one, XH, okay, X is a 4-dimensional vector. Okay, H is a 3-dimensional vector. So this is actually 3 times 4. Okay, and then your input is of a form 4 times 1. And then together, when you multiply this using matrix multiplication, you will get 3x1. So 3x1 plus 3x1, and then you do a 10H. 10H doesn't affect the dimensions. My HT here is 3x1. Yeah, so this is like some details of like how the matrix multiplication is done in order to get your hidden state. Okay, this is used quite a lot in neural networks. It's also used a lot in transformers as well. This is just a standard packaging for matrix multiplication in order to get a certain dimension. Okay, so lastly, we have the output layer. So you can notice that this output layer contains 4 numbers here. Okay, anyone want to guess what these 4 numbers represent? Yeah, I give you a hint. Okay, these 4 numbers are used for classification. So remember what we did for like CNNs the last few times. Like when you have 4 numbers like this, generally what do you expect them to represent? Anyone want to try?
The likelihood for each number to be 1.
Correct. So these numbers that we see over here, they're actually called the logits. Okay, which basically like the higher the number, the more likely it is. Okay, of course, the logits will need to go through another layer. Okay, so this is a refresher. Okay, in order to be like probabilities. Okay, what is the common activation function used to transform this into like a series of numbers that sum to 1? Anyone start with S? What's sorry? I heard the answer already. Okay, I'm just gonna write out the answer. All right, I think I heard it. Okay, but the person probably too shy to say it. Okay, so usually people use this softmax activation function in order to get the probabilities. And that's right. So in this case, what we want to do is we have, so by the way, this is what we are going to code for the coding example later. So we have an input character here, and then we have a target character, which is like the next letter. So H, you want to predict E, and then given the next letter E plus the previous hidden state here, you want to predict L. Okay, so this is how we do it. So over here, you see the highest number is 2.2. And then if we do softmax, this should be the highest probability as well. This corresponds to, remember, we have our one-hot encoding being like that, HELO. So this is actually an E, this is actually an L, this is actually an L, and this is actually an O. So you can see that in this toy example here, the model predicts perfectly. Okay, if you get this kind of model in real life, I think it is quite rare. Okay, because real life, unless you have trained it well, your training distribution is exactly the same as your test distribution, you should get something like that. Okay, but if not, you will have like 1 or 2 errors, here and there. Okay, so this is one example. Thank you, Singy, for your answer just now. Singy, right? That's all.
Yeah.
Okay, so now I move on to another example. It's called character level language model sampling. Okay, so it is very similar. Actually, these two are similar to what we're going to do later. So this character level sampling means this was how you train it. Okay, you train it using, okay, so if you use softmax, then you will use this thing called categorical cross entropy to train the loss function. So after you train finish already, how do we use this model to predict the next character? Okay, very simple. Again, the same thing. We do one hot encoding or embedding. Okay, one hot encoding, go through the hidden layer, go to output layer, do a softmax, sample. Okay, so this sample is very interesting. So you can sample in two ways. Okay, one way is you just basically take the highest number. It's called the argmax. Okay, what happened to my drawing? Yeah, so one way is you can just take the highest number here and then always generate this number. Okay, so in this case, this is H, E, L, and O, right? So it means that if you were to use like argmax, we will always generate O. Another way is you take this probability distribution, you can smooth it or you can sharpen it using some temperature. Okay, and then you just do a random sampling. So over here, they did a random sampling. So although E was like 0.13, okay, but there's still a 13% chance that you can sample it. So we sample E. Okay, and then the interesting thing about this sampling is that this output E, okay, is not forgotten. Okay, this output E actually goes back to the input of the next character. So the input is driven by your output. So it's a very interesting use case because whatever you generate in your previous time step will be the input for your next time step. So in some sense, it is a self-fueling model. Yeah, you don't really need any data. I mean, after you train, you can like generate the text for you. Then you pass it through the network again, and then you get this L here. Again, L is sampled with like a probability of 0.05, which is quite unlikely, but yeah. So actually, you can see that this sampling method, you can repeat again, and then you can do again. Eventually, you will get a string of words, hello, and then maybe at the end, you might want to train it with a CLS symbol or a symbol that tells the model to, stop generating. So, stuff like machine translation, they also use things like this. They keep generating the output until you tell them to stop. Okay, but for machine translation, they normally have another loss function called perplexity. Perplexity means how complicated the output is. So typically it's penalized by length. The longer your sequence, the higher your loss. So it tries to make the model try to output the correct answer with the fewest words possible. Yeah, it's something like, those kind of summarize the passage that you do in English or like, yeah. So this encourages the model to use shorter sentences or shorter characters. Okay, so that's the worked example. Okay, now I would like to do a caveat here. Okay, what I'm about to share with you right now is not really required in order to understand like what RNN is. But if you are very keen to know the full math behind it, okay, we will see the math now. Okay, but I'm not going to go through every single thing, okay, because this is not a math course, okay. But I just want you to know how this roughly works. Okay, so we have three main kinds of RNN architectures right now. Okay, we have this vanilla RNN. Okay, they always like to use vanilla for original models. Okay, vanilla that doesn't refer to the ice cream flavor. It just means, actually maybe it does, because people think vanilla ice cream is plain, right? So it's just basically the plain old RNN, vanilla RNN. So this basically is what we have been describing earlier. Okay, the thing has been cut off a bit, but this is actually H and this is HT. Yeah, so basically I will go through this in the next 3 slides as well. This has the vanishing or exploding gradient problem. Okay, because if we were to take in like the gradients from this part here to this part and so on, you will notice that if we were to, you all know like some like for example, if you want to multiply a gradient by 1.02, okay, if it's only like going before 5 layers, it's fine. But what will happen if we do this for 100 layers? Okay, so you can imagine if you have something like this, like in the backpropagation, okay, what will happen is that this one will go to like tends towards like a very high number. Yeah, I don't have a calculator. I cannot calculate this out for you, but you know, if you were to like multiply the gradient by like 1.02 each time, you will get a super high number. What if we get something like this, 0.9 or maybe 0.9 to the power of 100? Okay, can you see that 0.9 to the power of 100? Okay, 0.9 times 0.9 is like 0.81, then 0.7, 0.6543. It goes actually to 0 quite fast. Okay, anyone see the problem here? If we were to use like a lot of these cells together and then we stack them up into one long chain, when we actually do our backpropagation all the way back, you realize that you actually cannot update the stuff at the starting anymore, because either it goes towards a very high number. A high number is called the exploding gradient problem, or it goes towards a very small number, which is called the vanishing gradient problem. Okay, so what do people do to solve this? Right? Of course, we cannot just stop there, right? So people invent this thing called gates. Okay, so we have a few gates here. The forget gate. Later I'll go through some of them. Forget gate, output gate, input gate. Yeah, so we have some gates here used to like gate the gradient going through each time step. LSTM even more complicated. Instead of having a hidden state, they also have a cell state. Yeah, so it just makes things even harder for people to understand what's going on. You know, when you look at this, it really looks quite complicated, right? You look at this, it's like, what's going on here? Yeah, so yeah, I read through the original paper for LSTM. They use a lot of math, and to be honest, the math was more confusing than it helped. Yeah, so actually this diagram is actually more helpful than the original paper. Okay, GRUs, thankfully they try to reduce the complexity of LSTM. They have there are fewer gates. Instead of like forget input output, they only have like the remember gate and the update gate. Yeah, so much easier. But the idea is, as I said, I'm not going to talk through more of the math, but I just want to talk through the idea. So the idea of preventing the gradient, or rather not really preventing, but minimizing the gradients vanishing or exploding, is to use gates. Okay, you can see that the gates are actually sigmoid gates. Okay, so again, a question for you. Why are the gates sigmoid? Anyone can hazard a guess? Let me just give you the sigmoid activation function so that you can like roughly. So a sigmoid activation function is like that. Yeah, I know I draw it a bit slanted, but it goes from 0 to 1. And this is like maybe your input X. And then this is like sigmoid X. Yeah. Anyone want to guess like why are my gates using the sigmoid activation function? Why not use other activation functions like ReLU? You don't have to be right, you know, just guess. Why do you think people use sigmoid activation function to do the gating? Anyone? Yeah, just say something. Yeah. Okay, so I take it as is too difficult a problem to say. Okay, but I mean I thought about this for a while and I figured it out. Okay, why sigmoid? Okay, you know, it's like your on-off switch. Okay, when it's off, you don't want anything to go through. When it's on, you want everything to go through. So a sigmoid gate is like your on-off switch. So your off is of course when it's at 0 and your on is at 1. So you let the model parameters determine whether or not you pass through the entire information from the pass or you pass through nothing at all. So it's either 0 or 1. So, and I mean, you can also use other activation functions that range between 0 to 1. But sigmoid is the most commonly used for gating. And it helps because imagine you have something like this. Remember we talked about the exploding and the vanishing gradient problem. If you have something like this, like 1.0 to the power of 100, imagine you have a gate somewhere. If let's say I were to do a gate, then it may not be 1.02 to the power of 100. It might be like, after you do a gate, it might be like 1.02 to the power of 4. Then after that it resets. This gate goes to 0. Then after that it goes to like maybe 1.02 to the power of 5. Yeah. So with gates, you don't exactly have the gradients go through all the way. after a while you hit the bottleneck because of the, or not bottleneck, it will hit the gate. And then if the gate is shut, the gradient doesn't flow through anymore. And surprisingly, this stopping of gradients or restricting of certain gradients help the model to actually learn better. So we go back to like the problem of just now, okay, let me use a better color. So we go back to the problem of maybe like just now, the cat which sat on the rack landed on feet. So for a problem like this, you want the gradients from the cat to go all the way to like that word, right? So what you can do is you can like, you can just cancel this part here and then come straight here. So I mean, in terms of like LSTM, we have this like forget gate. Okay, and the forget gate is called forget gate for a very good reason, because you forget what happens in the past. So for example, in this cell state here, you will forget whatever hidden state there is at the, you'll forget the hidden state here. Okay, because if my forget gate is closed, okay, is 0, the cell state, okay, wouldn't, oh sorry, if the forget gate is on, is 1, okay, your previous cell state, okay, will be equals to 0. So it forgets the previous cell state and is conditioned on the input as well as the previous hidden state. So this forget gates helps you to like do stuff like forget all these words here, so that your gradient flows straight away from the cat to this thing here. You can solve it. So LSTM actually helps this quite a lot. Okay, GRU has the same kind of function. GRU, this is called a reset gate. So, sorry, this is the update gate. So in the update gate, yeah, I kind of suck at drawing words with my mouse. Okay, but the update gate, what it does is that based on the previous cell state, and sorry, based on the previous hidden state, as well as the input, okay, what it does is that it decides, okay, whether or not to forget the past cell state. Okay, then if it chooses to forget the past cell state, then what will happen is that you will then pass in this part here, which is the current input. Okay, so there are a few things. Then this remember gate is basically whether or not to remember, okay, whether or not to remember this last cell state. So there's a remember gate here. So there are some mechanisms working. Okay, so this all help it to like filter whether or not to remember past information or not. So all these gates do that particular role. Like forget gate helps to forget like previous cell state. This input gate helps to see whether the current input xt, is it worth remembering or not, because the input gate is applied to the input here. The output gate here, the output gate is basically to just check whether or not to remember the previous cell state, because you can see that the output gate, where's the output gate applied to? The output gate is applied here. So it chooses whether or not to remember the previous cell state, because then it will then be passed on to the next hidden state. So that's the output gate. Okay, I drew quite a lot of lines here. Okay, it's because I think the idea behind gating is really just basically selecting what information to pass through to the next time step. Okay, why are LSTMs and GRUs designed like that? To be honest, we all don't have a clear idea why to, because some people just configured certain parameters, certain model parts, and this sort of work. Yeah, but of course there are variants of this. But the key idea behind all these variants is that there's some form of gating that's conditional upon some of the past inputs. So you gate the future inputs based on the past inputs. Okay, so that's LSTM and GRUs, and this is how they solve, or this is how they mitigated the exploding and vanishing gradient problems. Okay, so this was quite heavy. Okay, and the benefit of me going through so much at the beginning here is that I don't have to go through any of this now. Okay, so feel free to look at the math in your own free time. Okay, but whatever I covered, this vanilla RNN, you can look at the hidden layer and the output layer. Basically, this diagram sort of summarizes what you see here. Long short-term memory, you have forget, input, and output gate. Also, based on this diagram, you can already see what this gate is applied to. Like this gate, when you do the multiply, it applies to this other branch here. So you can choose to look at these equations here for a clearer understanding. But to be honest, just looking at this, this is called the circuit diagram, should be enough to let you understand what's going on already. Forget gate, input gate, and output gate, 3 different gates for long short-term memory. GRUs, you have the update gate and the reset gate. This Z is the update gate, and this is the reset gate.
So actually each cell hosts about 3 to 4 more weights than a normal vanilla RNN.
Yeah, so over here you can see only has U and W and V. Okay, of course, this W is for output, so we take out. So it's just U and V. But LSTM, you have like for each of these gates, you have a weight vector. So you have like 4.
And each weight during
And each
backpropagation will be tweaked, right?
Yes.
Each weight.
Yes.
Doesn't that mean that this layer for long-term short, the computation is a lot more than a normal RNN?
Correct. So it will take a longer time to run. And that's also the reason why people have invented this gated recurrent units. This is a more recent invention. They try to summarize whatever this is done here. So I mean, there are some parallels, like this reset gate could be like the forget gate, because like it makes you like forget what is in the past cell state. And they try to combine the hidden state and the cell state. To be honest, I don't know why there's a need for another hidden state, because like hidden state is hidden, but they just do 2 different states. I suspect that this actually helps with the model, is because what I say about the bottleneck problem of the hidden vector. The more you dump information, the harder it is to retain all the information. So maybe this cell state helps to contain more information if you think from the information theory perspective. So this might help. Okay, but of course, in a gated recurrent unit, you don't really have the benefit of 2 different hidden vectors, but you can make the hidden vector much larger. Yeah, that might solve the problem as well. Yeah, so yeah, they combine the cell state and the hidden state to be 1 hidden state. Yeah, but and then they also combine some gates to like make it a reset gate, where is either use like the previous input, or we use the input layer XT. But you see this there are 2 things, right? This XT over here actually also has this input here, but this input here is governed by the reset gate. Yeah, so actually it's quite complicated, this architecture as well. Yeah, why this works? To be honest, I think it only works because you gate based on the previous inputs. Okay, I mean, you can do various combinations of how to gate, but I think as long as you apply some form of gating, you would solve partially some of the vanishing or exploding gradients, and this could be the reason why this is better than RNNs. Any questions here? Okay, so as what I said, I'm not going to cover all this math here. Please feel free to read up on yourself. It's from this site over here. Of course, in most deep learning books, they will also cover, this site also talks about the backpropagation equations, but I omitted it in this slide because if not, it will take about 2 slides to fill. Okay, it's actually quite long, the backpropagation. Okay, so instead of giving you math, I give you diagrams. Okay, so I encourage you to look at the math if you are brave enough. Okay, it gave me a headache the last time I looked at it. So good luck. Okay, so backpropagation, how we do backpropagation is this cool name called backpropagation through time. Actually, it's no different from a normal backpropagation. If you like treat this as an expanded network, is basically whatever forward operation, you also go backwards. Like this one goes backwards here, goes backwards here. So you just reverse the direction of the arrow, you get your backpropagation. So over here, you can go backwards like that. Okay, so you can see that there's one stream of backwards flow arrow like that you can use it to update. You don't update the inputs, okay, but you update the weights to the inputs. So you can see that your arrows flow in the reverse direction of your operations. So this is arrow number 1. Of course, you can go all the way to the end here, but imagine what will happen if you do that. You go through 100 time steps. You need to backpropagate 100 time steps. And that means you will take a very long time to do your backpropagation. Okay, so that's why people have come up with this thing called truncated backpropagation through time. It means that instead of doing for the entire network, I have a cutoff, like maybe in this case, 6 time steps. I look through the past 6 time steps and I backpropagate all my weights over that. And take note when you backpropagate your weights here, actually you are doing a concurrent consecutive update because all these weights are the same because you use the same cell. Yeah. So this is only one gradient flow, by the way, one gradient flow from this loss function. Can you imagine that there's another gradient flow here? Can you imagine this? You have to do for all the gradient flows, So this is gradient flow number 2. Okay, I'm not going to draw gradient flow number 3 and number 4, number 5, number 6, because I think there's too many colors to see, but you can see that you also have a few more gradients over here that I haven't drawn yet, but you also backpropagate all this. So a good way to find out how to backpropagate is you look at the forward equation, you see where the arrow is pointing to, you just reverse the arrow and that's where you backpropagate. Okay, so backpropagation through time is just truncated. The truncated backpropagation through time just cuts off the backpropagation step halfway so that you update less. Okay, but in so doing, you train the model faster also. Because you go all the way to the back here, and it also helps to solve in some sense the vanishing or exploding gradient problem, because you don't actually need to multiply like so many times. Yeah, so this is how we do backpropagation through time. And then the main weights that we update are the weights that are in the recurrent neural network, which is given in the previous few slides. You can see those weights. So like, sorry, you can see like these are the weights, the parameter matrices we use. We update all these parameter matrices here. Okay, these are all tradable parameter matrices that we update using backpropagation through time. So a very cool sounding name. You don't exactly time travel, but you just backpropagate through your entire forward flow of the network. But because your forward flow of the network is sequential, it goes through time. So the backpropagation goes in the reverse order of time. So there we go. It's like time travel, right? Backpropagation through time. Okay, it sounded quite cool, so people stuck with it. Okay, but it's actually just backpropagation. Okay, questions? Okay. So now we go through the work example. Okay, I have about 15 minutes more. I hope you all can stay a little longer because I like to cover the code as well. So we'll cover through how to generate text using a character-based model with an RNN. So this is the main network. Okay, it looks very complicated, but let me just, this is like your character level. Remember just now we go through the one-hot embedding. Now we use an embedding layer. Embedding layer is nothing more than just like for every like, so it's something like this. For every vector that you have, like this is your character, maybe this is like H, E, L, O. For each character you map to a number. Okay, and then each number will then go into an n-dimensional vector of like maybe some numbers like 0.1, 0.3. So what these numbers represent is basically the location in the embedding space. The embedding space is like a map. I wanted to do it the next session, but I'll just draw it. Like maybe H and E are more like semantically related. L is somewhere here, O is here. So having a map like this, when you map like different vectors, okay, what this does is that it basically helps you to, like, if you have similar letters, you can interpret them in the same way. Okay, this applies actually more for our words, but characters you can also use it. Okay, so you can have like embedding space. Maybe H and E are more similar. I mean, this is just an example. Yeah, this is an embedding space. So this embedding space. Yeah, so the details of how to do backpropagation for this, if you are interested, the TensorFlow implementation for this is they actually do a one-hot embedding. So they do a one-hot, okay, one-hot embedding, and then after that, you can have then after that, this entire vector here, you can then multiply the one-hot by this vector, and then based on your one-hot embedding, you can get the correct like n-dimensional embedding space. Yeah, so it's basically matrix multiplication. Basically, Google is just using matrix multiplications to solve a lot of things. So yeah, to do the backpropagation, as long as you do a matrix multiplication, it is differentiable. Simply put, yeah. So the way we do the embedding training as well is also using matrix multiplication. Okay, so that's all for the embedding layer. I just give you some context so that you can understand what's going on later. So we use a GRU. A GRU is what we saw just now, gated recurrent unit. We have a starting state, and then we just basically pass in all the states one by one. And at each state, we take the hidden state here and we get an output. So the output is basically going to be a letter, right? So you pass it through like a dense layer. which goes through the logics. The lens layer is like maybe if you have an input vocabulary of HEL0, HELO, your dense layer will have 4 nodes. Okay, then after that, from there you pass through the logics. You use softmax. You can get use categorical cross entropy loss. You can do that. If you have no idea what this is, refer to the earlier slides on CNN. It's the same loss. Okay, so this is how we train. So given all the input characters, we predict the next characters. That's what we train. Okay, during testing. So actually it's the same as what we saw in the work example. During testing, what we do is we take in the letter, do a random sampling from the logics or from the softmax distribution here. We take the letter, pass as input, sample again, pass as input, sample, and so on. And this is how we will generate the text. So, all right, let's run the model. Let me stop my share and load my. Okay, can y'all see this text generation? Thumbs up if you can see this text generation using RNNs. Okay, so don't mind me, I'm just going to spend like 5 to 10 minutes just running through this code. Okay, this code was adapted from the TensorFlow tutorial, but I found the tutorial too difficult for understanding. So I revamped most of it. Yeah, but the idea is the same. Okay, so let's do it. Okay, import TensorFlow and other libraries. Okay, then we get this file called the Shakespeare text. Basically, it's like I think 3 of Shakespeare's books, okay, combined together. And then the idea is that through some training, we want to generate Shakespeare sounding like text. Okay, then we read in the file. This is to read the file stuff. This open thing is a Python thing. Okay, so we have 111539 4. Oh wow, so many characters. So we can see like the first few characters. We can even see a bit more. Like I can just show you like this is how the text look like. First citizen. Before we proceed any further, hear me speak. Speak. You are all resolved rather to so and so on. So you can see that this is the text that we have. Okay, then we can see the list of unique characters that we have. So I use the set operation, which basically does unique characters. So there are a total of 65 characters. You can take a look at what are the characters, basically the letters and a few symbols. Okay, not all of them are there. I mean, not all the symbols are there, only a few, like you can see at the start. Okay, then this is something that I created. Okay, so basically I create a dictionary that maps, okay, a character to a number and also a number to a character. So I just show you like maybe the car to num. Okay, I just print out this for you to see. So basically given like the characters, I map it to a number. Okay, using this code here. And then I also do an inverse. So TensorFlow does have a helper function to do this, but I find it very hard to understand what's happening. So I think this is clearer. Okay, so this part here is a number mapped back to the character. Then we'll do some form of processing here because as what I said earlier, if you were to just give it letters, it is not differentiable. So if you have to learn anything about deep learning, remember that it deals with differentiable functions. So if your input is not in a differentiable format, you need to make it so. Okay, either through one-hot encoding or like embeddings, something like that. So now we do some form of, okay, this is a helper function that takes in a list of indexes and comes out the characters. This takes in the characters and comes out the index. And if this gets the indexes, this gets back the text. Okay, so this actually should be get indices. Okay, I labeled it wrongly, but yeah, basically the idea is if you have a list of characters, you want to get back the indices. Okay, so actually this one should be like 0 or something. Yeah, I'll change the code later. Yeah, so but I didn't affect because the default didn't need to get used. Okay, so what we do is we have this data set from tensor slices. Okay, which basically what it does is that from all this text I convert into indices from using the get class. Okay, it should be get indices actually. It's okay. Then we can see for the first 10 characters of the text, you know, the first citizen, it get maps now to 18, 47, 56. These are like the indices that are based on this. So like 18 is F. first, then I, small letter I is 47. Yeah. So something like this. These are my sequences. Okay, then what I do is I want to split them into batches of 100. And over here, I just need to use this batch operation from the dataset operation. So the actual sequence is like this: first citizen, and the indices are like that. Okay, then what I want to do next is I want to split this sequence into the first 100 and the last 100. So this is a sequence of 101 characters. First 100 and last 100 is because the first 100 will be the input set and the last 100 will be the target set. Remember, we always predict the next character. So the target text will always be like one character to the right of the input text. So we can see what this does. So the input shape is this. And then for like given the first input F, you want to predict the next character I. And that's why we do it like that. Okay, this is some code to create the data set. So we shuffle, we do the batching. Okay, with a buffer of 10,000 so that we don't load the whole data set. Okay, why we need to use the data set? Because I actually tried to remove the data set and it took 12 minutes to run the code. So if you put the data set, it runs in like 10 seconds. So the data set actually helps to prevent a lot of overheads because you don't need to load the entire data set at one go. You load on the fly. You load to fill up your buffer. As long as your buffer is filled up, it doesn't load anymore. So this is something that helps to optimize the code. Okay, this is the model that we went through just now. Okay, so we have 3 layers: embedding, GRU layer, and the dense layer. So first we have defined some parameters. We do the layer model. So it's input. Okay, embedding. Actually, we can omit the input for sequential. It will still work, right? Because TensorFlow will automatically determine the input size. Okay, embedding, which is the size of the vocabulary, which is the number of unique characters, and the embedding dimension is like the n-dimensional space you want to project it to, which is 256 dimensions. We can change this as well. Then we have a hidden unit of size 1024. Again, it's tunable. Return sequences equals to true means that I return all the intermediate outputs. Okay, if you don't put this to be true, it only returns the final output. Okay, so this is why we use this. You can also change this to simple RNN or LSTM to just test out what works. Okay, I tested all of this. LSTM actually works the best. Simple RNN didn't work too well. I mean, as expected, due to the gradient vanishing or exploding problem. So we have the dense layer at the end in order to get the softmax. Okay, let's run this. Okay, this is the functional code I provided in case you are interested to find out. Okay, then we do a model.summary to see what this is. We can do the plot model again to see how this works. Input, embedding, GRU, dense. Okay, of course, this goes through time, but then we never really see it. Okay, yeah, thanks, Teju. I got it. Yep. So let me just end within 5 minutes. Don't mind. Here we have the model.compile. So this compiles using Adam optimizer, sparse cross entropy, and then have an accuracy just to see how accurate it is. So I'll give you an example of how the input outputs for this data set would be. So with the batch, the input shape is of 6400 because there are 64 different batches. The batch size is 64, so 64 different input sequences of 100. And the output is also 64 different sequences of 100, which is the next character's output. We do a model.fit, which basically trains the data set for 5 epochs. You can train more if you want to basically have more precision. Okay, maybe I'm just going to train for this one. Actually, I do have another one at the bottom. Okay, so while it's training, let me just go through the next part of the code. So next part is the generation for the text. Basically, given the input text, okay, we feed in the model and then we come out with the logits over here. So this is given here, predicted logits. We only use the final one, which is the next character. And then we do a random sampling. Okay, so there's this temperature here that we define. If the temperature is smaller, it's closer to argmax. If the temperature is greater than 1, it's more random. Don't use this, it doesn't work very well. 1 is like original softmax. Yeah, so that's how we do it. Okay, now epoch 3. Okay, then after that, we will do the testing. Okay, so okay, I don't really think we need to wait for this. Okay, but the idea is that if we generate the text, we'll get something like this. So apparently when I train this to like generate the next 400 characters, It appears to like memorize this like phrase called the sentence of the season. I have no idea where this came from, but you train it for longer, you should get better performance. So you just try it out, train the model, see what you get. Okay, so you can increase the number of characters. You can even look at all the characters before that. I just set it to 100 because it takes quite long if we were to use everything. Of course, if you look at the original code that you have in the TensorFlow website, it is much faster than my code because they actually have a custom model that can take in the previous input state as well. I just didn't do it here because it will make the code more complicated. So do check out the original code if you want to find out how to do it with a much faster runtime. Okay, these are some challenges that I have. So try to use your own data set, okay, to see whether you can generate as well. Try to change to LSTM RNN. It's quite easy. Just change it to see what is better. See whether you can improve the output plausibility by modifying either embedding dimensions, RNN units, or epoch. Yeah, so epoch actually is the easiest. You train for 30 to 40 epochs, your output is quite good. Okay, so let's see whether we are done running. Yes, we are done. So we can. So you can see if we have Romeo, the next character is like I. So let's see. We start with Romeo. And then we see what's the output for this. So different already. What say you shall be me to the present? Sounds not bad actually, but you see, in terms of the longer range semantics, it doesn't really capture it because King Edward IV has been talking to himself for the next. So if you train it longer, it will have a better kind of output. So let's run again to just see what's the next. You see over here, there's a season of the people again. Yeah. Yeah, so yeah, it is not that great right now. It will be better if you run it for more epochs, which I don't think I want to do because it takes quite long to train it. So feel free to experiment on your own. We can even change the starting text. Okay, we can even change it to like, I am the prince of, okay, let's say I'm the prince of the people. I mean, it really depends what you want to use, but let's say something like this. Or you want to give a suggestion that I just run it, we see what it generates. Yeah.
Okay, I think so we can try on our own. We run out of time.
Okay, sure.
Yeah.
I'll just conclude. Give me 1 minute more to conclude.
Sure.
So there's this thing where I experiment also to just like, instead of using embedding, we use one-hot encoding. So in this case, we can use the category encoding layer, which is the one-hot encoding, map it to the data set. Okay, and then we do the same thing again. The model, we remove the embedding layer, we run it, and then you can generate the text. Okay, and what I found out is that if we use one-hot encoding, actually the performance is actually worse. So actually the embedding layer does have some help in terms of getting the right semantics out. So yeah, yeah, that's the end for today. I hope this was interesting. Feel free to try out the code and generate your own text. Right. That's all from me. Thanks.